All right. Good morning, everyone. Louder. It is Wednesday at reInvent, so welcome. Welcome this morning. You are in the EBS deep dive. With me on stage,
I'm Mark Olson. I'm a principal engineer with EBS. Been here for 8 years and hope you guys are having a great reInvent this year.
Yeah, and I'm Ashish Palekar. I'm a product manager on the EBS team. Our world revolves and rotates around customers. And just by show of hands, how many of you have used EBS? Everyone. Good. Thank you. Right? And thank you for, as you can see, we have coverage with a wide number of verticals, wide number of use cases. And so we're going to try to do our best to give you the wide gamut of what EBS does and how it does it. Our agenda for today's session, Mark and I do this deep dive. We've done it for, I think, 2-3 years on the trot, Mark. Based on feedback from you from last year, we're going to change things around a little bit. And what we're going to do is focus on specific areas and try to hone in on the improvements we've made, but also our best practices and recommendations in those areas. And I think the feedback we get, a lot of your developers want to use these tips and tricks in your environment, and so that's what we're going to focus on. I'll start off with security and encryption. Then Mark will dive into performance, availability, durability. I'll come back in again, talk about saving cost. And then we have a real-world use case with our customer Teradata to walk you through how they put all this together for their solution. We have a ton of content to get through, so let's get started. Mark and I will be here after the session, happy to answer any questions you guys might have. So with that, let's talk about security and encryption on EBS. So when we think of security, EBS integrates with the Amazon Key Management Service. We use AES 256 encryption, and we use customer master keys. Right? And there are a few things that are important to understand. When an EBS volume is encrypted, it implies that data at rest inside the volume is encrypted. Data moving between the volume and the instance is encrypted. Snapshots created from that volume are encrypted. And volumes created from encrypted snapshots are also encrypted. In other words, that boundary of encryption allows all these other capabilities to flow directly. How do you encrypt? Well, if you go to the Create Volume console, and right there you can see sort of the options there. And one of the options is to create an encryption, right? And select a master key for that. How do you select a master key? You go into the KMS console, and within the KMS console, you can now create a new KMS master key for EBS. Creating the master key allows you to define key rotation policy, enables CloudTrail auditing, controls who can use the key, controls who can administer the key, right? And once you define that key, you can now select it within that master key setting in your Create Volume console. From that point, as you add storage, you can just select the encrypted option and select the key, right? If you're like me, and you like CLIs, then that's how you do it on the CLI, right? You can select the run instances command, select block device mappings, and in the mapping JSON, specify the key ID that you want to use, right? One question we get asked often, if we use encryption, does my EBS optimized performance get reduced? The answer is straightforward, it's no, right? The rated performance on our 4 series and 5 series of instances, which is the C4, M4, R4, C5, M5, R5, is exactly the same, whether you're encrypted or not encrypted. Right? So in other words, encrypting an EBS volume does not reduce your rated performance on those instance families. Right? And so that trade-off doesn't exist. Later on, Mark will talk about why that is. But it's important for you to understand that you're not making a performance and encryption trade-off. Part of the EBS journey is also snapshots. And within snapshots, while we won't go into depth in snapshots specifically, snapshots of encrypted volumes, as we talked about, are fully encrypted. volumes created from snapshots that are encrypted are also encrypted. You can encrypt an unencrypted snapshot by copying it, and you can re-encrypt a snapshot while you're copying it as well. So why are snapshots different? And this is hugely important because of some of the security implications. Snapshots can be shared across accounts. They can be copied across accounts. They can be copied within accounts. They can be copied across regions. And snapshots are used to create armies, right? And it's super important to realize that that changes some of the security posture related to snapshots. So let's look at sharing of snapshots. When sharing snapshots, you can go down the Modify Permissions tab as you think about the Create Snapshots console. Or if you like CLIs, here's the CLI command to do it. You can describe the snapshot attribute and create a volume permission. The permission tab there actually is permission for sharing it publicly, and I'll go into that a little bit later. Here's what this looks like on the console. On the console, sharing looks like you have two options. You have public and private, and then you have private that you can share with an account. Be especially cautious about the public sharing, right? When thinking about sharing snapshots and armies, public sharing is a reasonable use case for armies, right? But be super cautious about why you're sharing those armies. Think about marketplace armies. That's a reasonable use case. In almost every other case, you want to share it with a specific account, right? And if you want to launch a volume from that snapshot, one of the things that we see often is that customers don't copy that snapshot into their region. So you need the snapshot in region in order to launch a volume from that snapshot. So be aware of that. One question I get asked often is, how do I check what my snapshot sharing permissions are? Two ways to do it. Here's on the console. Within the snapshots console, there is a permissions tab. You can click on the permissions tab, and as an example, here's a snapshot that I'd made public. That is an example of the snapshot that is public. If you pull the describe volume, the create volume permissions, you can see that the group is all. Again, that's a publicly shared snapshot. Again, very few reasons to actually do that. Make sure you understand why you're doing it and how. All right, so we talked about copying snapshots and how you can encrypt and re-encrypt. Let's see how you do it. So you go into the snapshots console, pull down the copy snapshots tab, and within the copy snapshot, you can specify the encryption, right? If doing it via CLI, that's how you do it. But basically, you can select if it's an unencrypted snapshot, you can encrypt it. If it's an encrypted snapshot already, you can go change the key. What's a use case for that? This is a use case that we've discussed with multiple customers, and we see this pattern a lot. Customer has snapshots. For that particular snapshot, they then copy it across regions, and then in the second region, using the resource level permissions that are supported on Snapshot, take away those permissions and then lock it down. Why do they do this, right? First, multi-region to sort of protection against regional events. If there is a regional event, this protects them against it. But the locking down of the permissions is so that they can protect against malicious or unintentional delete of data, right? And we see this pattern a lot in the copy snapshot use case. So earlier this year, in May, we launched 3 features guided by feedback from our customers about how to make encryption for snapshots easier. What I'm going to do is walk you through those 3 features and how they're useful to you. So 3 features were launching encrypted volumes from unencrypted snapshot or armies, share snapshots encrypted with custom CMKs across accounts, and then encryption by default for an EBS account within a region with a single click. Let's walk through each of these. So encrypted volumes from unencrypted snapshots or armies. So previously, if you had an unencrypted snapshot or army, what you would do is copy and encrypt it into a snapshot or army, and then launch an encrypted EBS volume from it. Show of hands, how many people have done this? Quite a few of you, okay? A bunch of you complained to us about this and said, why do we have to do this? It takes time, it takes effort, and really we don't want to do this. So now, with the new feature that we launch, what you can do is take an unencrypted snapshot or AMI, with a key, directly launch an encrypted volume. So no more copying of the snapshot and re-encrypting it for this particular use case. You can do exactly the same thing if you want to change the key. So how do you do it? Remember that create volume console we were talking about? Same thing here. Specify create volume. Within that create volume, now as you're launching a volume from a snapshot, you have an additional option to encrypt the volume. Right? And so if you're like me, like the CLI, you can use the create volume command and specify the -- encrypted flag. And that's it. The volume will now be encrypted from an unencrypted snapshot. So sharing of the encrypted snapshot or AMI across accounts. Okay? Here's what you did previously. If you had a snapshot or an AMI that was encrypted with a custom CMK, you would have to copy that snapshot across accounts. Okay? You would then create volumes from those snapshots and then get to an encrypted volume in account 2. Okay? By the way, encrypted snapshots could only be copied across accounts. They couldn't be shared. So what we've now done for snapshots or AMIs that are encrypted with custom CMKs, you can now just share them across accounts. Right? By sharing them across accounts, you can now launch the encrypted volume across that account. So in a single step, you can launch an encrypted volume in account 2 with a snapshot in account 1. One note here, this only works for snapshots that are encrypted with custom CMKs. This is not currently supported with snapshots that are encrypted with default CMKs. How do you do this? So step 1 is you have to share the key. And the way to do this is you go into the KMS console, and within the KMS console, you specify the key and give permission to an account for that key. That account that you want to launch the encrypted volume in, you can share the permission for that account. From that point on, you can launch a volume by specifying the key within the target account. And that's it, right? So you can go from taking an encrypted volume in one account and encrypt a snapshot in one account and launch an encrypted volume in a completely different account, all in one step. These features are independently useful, but they're even more useful together. How? So here's how. Let's say you had an unencrypted snapshot or AMI in account 1. You now have to copy that snapshot, re-encrypt it in account 2, and then launch the encrypted volume in account 2. Right? With these two features, here's what that looks like. You have the unencrypted snapshot or AMI in account 1. You can launch a fully encrypted volume in account 2. Right? All in one step. And again, our goal is here to make encryption simple. So while this is simple, you still gave us feedback that this was not simple enough. Right? And so what we launched is a third feature, which is account-level encryption by default at a regional level. What's the problem? So many of you had come and told us, well, my business has a need to make sure that all my EBS volumes are encrypted. Okay. So the way that administrators used to achieve this was within the account, they would set IAM policies. So if your end customer launched an unencrypted volume, it would block it from launching unencrypted volumes. The second way that administrators used to manage this is actually by taking the unencrypted volume, creating a snapshot, copying and encrypting the snapshot, creating an encrypted volume, and attaching it back to the instance. Pretty complicated stuff, right? And part of what we didn't like about this was it makes it punitive from a usage standpoint, and so pretty much prevents customers from launching volumes when they should. And so the team worked hard and tried to figure out, okay, how do we solve this use case? And what we launched, and I'll show you how we sort of do this, is a single account level regional setting, right? And what it does is, with that single account level regional setting, all your new volumes in that account and snapshots from those volumes are fully encrypted from that point on. Right? There is no change to your existing workflows. And in fact, what you'll see is, even when you don't specify the encrypted tab, your volumes still continue to be fully encrypted. Right? So how do you do this? You think it's complicated, right? Well, turns out you go to EC2 settings, pick the encrypted tab, and within that there is now a setting that says encrypted by default, right? And you can then specify the default encryption key, and that's it. From that point on, all your volumes in that account, all your new EBS volumes in that account will be fully encrypted, right? Pretty cool to actually see how that works for you guys. So before I hand off to Mark on the performance side, if you remember nothing else from this security piece, two things that I want to make sure you take away with you. One, please monitor your access. Make sure that you're not sharing snapshots with accounts or publicly if you don't have to. And then second, account level encryption is literally a checkbox. Use it. Okay, Mark, yours.
Cool, thanks, Jake. So now that we know how to secure your data and your customers' data, we're going to talk a little bit about building your application. So we're going to start off by understanding your mission. And it's super important to understand what you're doing before we talk about how you're going to do it. So let's take a different example, not from storage or compute or technology. Say I'm planning a trip from Las Vegas to London Heathrow. It's about 8,500 kilometers, right? I gave you two choices of aircraft. We have the queen of the skies, the Boeing 747, cruises at about 900 kilometers per hour. Or we have the de Havilland Beaver, cruises at about 200 kilometers per hour. If that's all the information I gave you, I would bet that most of you in this room, unless you're an aviation geek, would choose the queen of the skies. But what I didn't tell you is that there's actually a Beaver convention in London. And so with all this data, we realized that we're going to take the Beaver instead, take our time going over there. It's going to take us a couple days probably. But that's going to be more effective for what our mission is. And so much like this trip, you guys all have different types of workloads. And so we're going to walk through a couple different broad categories to help you understand what might fit in these categories. But also, it's important to recognize that not everything fits in these nice, neat little boxes. And so one of the things that EBS enables is the ability to pick and choose. And we'll walk through how you do that. So EBS does have two main families of volume types today. We have our SSD-backed volume types, and we have our hard drive-backed volume types. And so on the SSD side, we've got GP2, general purpose, or our provisioned IOPS product. And then our hard drive products, ST1 and SC1 are available as well. And so which ones do you choose? So let's start off with database workloads. This is a lot of what we see. Most applications have some sort of data store behind them. Typically, this is where your performance requirements come into play. Mostly random I/O. Most databases, even if they're NoSQL or SQL-based, have some sort of write-ahead log or a journal. And that's going to be mostly sequential. But the real workload pattern is highly workload dependent, or the real application pattern is workload dependent. So what your customers are doing oftentimes drives the requirements of your database. So typically, we see customers have the best experience on SSD volumes here. But sometimes hard drive-backed products work well here. So let's dive into the two different SSD products. I start with GP2. This is a volume that we spent a lot of time with analyzing data, analyzing customer workloads, analyzing patterns, and developed it to achieve and to hit the right performance sweet spot for about 70 to 80% of the workloads. And that's why we gave it the general purpose name. So if you don't know and you want to start somewhere, I highly recommend you start with this one. And so it's got performance that scales with the size of the volume. Part of our data collection told us that the more data you have, the higher performance needs you have. And so this is 3 IOPS per gigabyte is what it scales at. For smaller volumes, you get a baseline, or you get a burst capability of 3,000 IOPS. For throughput, this is up to 256 megabytes per second. And we do that with the logical merge size. So if you're doing some larger IOs, we'll keep track up to 256K if they're sequential and try to make it so that you can achieve that throughput for you. You can provision these volumes from 1 gigabyte all the way up to 16 terabytes. And so these are good for boot volumes, low latency applications, bursty databases, just about anything, really. So we talk about burst. I'm going to give you a little bit of an intro to how it works, because a couple of our products do have this notion of burst. And so on GP2, you have a baseline performance, and that's your 3 IOPS per gigabyte. That's always accumulating every second of every day that your volume is provisioned. We fill up a bucket, and when that bucket gets up to 5.4 million credits, you can't accumulate anymore. Everything just kind of spills over. And then as you're reading or writing to that volume, you can spend those credits at 3,000 per second. And so that's how the burst works. And so the performance, like I said, scales with the size of the volume. We started out at 100 IOPS for all volumes. So if you're 33 gigabytes or smaller, you're going to get 100 IOPS. Scaling all the way up to 16,000 IOPS with just over a 5 terabyte volume there. And that's your baseline. You'll always get that. For volumes up to 1,000 gigabytes, you can burst up to 3,000 IOPS. And that's the 3 IOPS per gigabyte that is depositing into that bucket. So if we take an example of a 300 gigabyte volume, you get a baseline of 900 IOPS, but you can burst to 3,000. So when you need it, sometimes you might have some peak workloads, it's there for you. The question I often get asked is, how long can I burst? And so with 5.4 million credits, and you're getting 3 IOPS per gigabyte, it's actually a curve that's nonlinear. And so the bigger the volume, the longer you can burst. So that 300 gigabyte volume, you can burst for 43 minutes. If we go a little bit larger to 500 gigabytes, you've got an hour of burst. And then as we get bigger and bigger and bigger and approach that 1,000 gigabyte mark, you get a longer time period. So 950 gigabytes gives you 10 hours, or most of the day. Our other SSD-based product is provisioned IOPS. Now, the thing that's unique about provisioned IOPS is that you can provision the performance separate from the amount of storage. So if you need a lot of space and not a lot of performance, you can provision that. Say you need 16 terabytes but only 1,000 IOPS, you can do that. Or the opposite, at a 50-to-1 ratio. So if you need 100 gigabytes, you can get 5,000 IOPS on that volume. And so these are provisionable from 4 gigabytes to 16 terabytes, and we have that same 256K logical merge. There's no burst bucket on provisioned IOPS, and the other thing about provisioned IOPS is it's got a higher latency consistency profile. So this is typically good for mission-critical applications, things that have sustained workloads, less bursty workloads, and we'll talk a little bit more about some of what we mean by critical in a little bit. Moving on to media. So this is your rendering farms, your transcoding, any sort of streaming product. Typically, you have higher throughput requirements, mostly sequential, and pretty sustained, especially when you're talking big render jobs. So for these products, our throughput optimized HDD, our ST1 product, might be a good fit, and also not called out here if ST1 doesn't have enough throughput for you, provisioned IOPS with its 1,000 megabytes per second of throughput might be helpful. Most of the time, ST1, and here we'll talk a little bit more about that, ST1 is good enough for you. So much like GP2, this has a baseline that scales with the size of the volume. However, the scaling is different. We use throughput instead of IOPS on our ST1 volumes. And so you get 40 megabytes per second per terabyte, up to 500 megabytes per second. And then a burst that's designed to allow you to scan the entire LBA range a few times a day. And so you get that up to 500 megabytes per second. The difference on the burst with our hard drive back products, I don't have a slide dedicated to this, but I do want to cover it quickly. On GP2, the burst bucket is a fixed size. On our hard drive back products, the bucket actually expands with the size of your volume to give you that multiple times a day scanning rate. These are not designed for boot volumes, and you have a minimum capacity of 500 gigabytes, but you can go up to 16 terabytes. And on the logical merge, and what I mean by logical merge is we don't actually hold on to your I/O and wait for the next one to come in before we complete it. We just keep track of where it was. And if the next one looks like it's in the same place or sequential or the next LBA range over, then we'll count it as part of the previous I/O. And so this is good for large block, high throughput sequential workloads. Data and analytics. This is a common application. You've got log analytics that you want to do, Kafka, Splunk, Hadoop, maybe data warehousing, different type of database pattern. Typically, these are higher throughput requirements, usually sequential I/O, but not really sustained applications. So there might be some daily or hourly or weekly periodicity to it. And so these are good for one of our hard drive back products, either ST1 or even ST1, which is a little bit colder. This is designed for one complete scan a day. So the baseline throughput is lower, the burst throughput is lower, and it comes at a lower cost as well. Everything else is similar to our ST1 product. So we've got the 1 megabyte logical merge, 500 gigabyte minimum capacity, and up to 16 terabytes. File sharing is another common workload. So this could also be web servers, things like that. CIFS, NFS, maybe a nearline archive. Oftentimes, these are super low throughput, very bursty, unpredictable, but when they do happen, there's not a whole lot of traffic that goes on. And you're designing these with cost sensitivity in mind. And so for this workload, SC1 is actually a super compelling case for it. So how do you know if you don't fit into one of these buckets what your application is doing? Well, the first thing we can do is fire up one of my favorite tools, and I use this all the time to give me a quick glimpse of what's going on with an application. And so this is IOST. It's a Linux utility. And we see here that over the course, so I've had a simulated workload to one EBS volume. And on the read side, so this is the R/S is read requests per second, and then the read throughput, I'm doing about 25,000 IOPS and getting about 1,000 megabytes per second of throughput. And so that comes out to about 40K per request. So under that 256K merge size, under that 256K limitation. On the right side, much smaller I/O size. So I'm only doing 6 megabytes per second, 1,500 writes. And so this may simulate a database workload where you've got a small journal with small writes. On average, across the entire block, I'm getting 39 kilobytes per request, and that's averaging the 40 and the 4. And IOST represents this in sectors, in 512-byte sectors instead of K. So you got to divide by 2. But what I don't know, based on those numbers, is my workload sequential? Is it random? Am I just doing 40K, or do I have some larger thrown in? And so we've got a Swiss Army knife in Linux called blocktrace. If you really want to know more about your workload, you can run blocktrace and capture exactly everything that's going on. Now, there's a number of stages that go on with an I/O in the kernel, and blocktrace captures all of them, from submitting it to the queue, from when the queue picked it up, to when the device actually put the completion back on, and to when the application picked up the completion. And so it captures the time of every single step. That's a lot of data, and so there are some tools to parse it. BlockParse will take these binary dumps and parse them into a human-readable format and output them in a format that's more easily consumable. The BTT program that you see here is also a standard Linux utility, and it allows me to extract some interesting parts of that data. And for this use case, I just wanted to know the offsets and the sizes. So I had it write out the block offsets file. I wrote a quick little Python script to take that file and analyze and figure out sequentiality of my workload, and also bin I/O sizes. So I kind of had an idea of what my application was doing. And so I run that on my application, and it shows that my reads were pretty random, just a little tiny sequential, but a mix of I/O sizes, which is kind of interesting. So I've got 8K, 32K, and 64K I/Os. And then that write was mostly sequential 4K. Now, since these were intermixed, IOST didn't show any merging or any sequentiality to them. But with this, what I can do is I can identify maybe there's part of my application that's sequential that I can carve off. A lot of databases will allow you to put the journal file onto a different device. And so this could be a use case where I put the read workload or my data tables on, say, a GP2 or provisioned IOPS volume, and I put the journal on an ST1 volume, since it's a sequential workload. And so EBS allows you to mix and match like that. You can take an instance, you can attach any number of volumes of any shape, any size, any performance characteristics, and really fine-tune what your application is doing. So we're talking a little bit about instances now. Instances are also important to the mix. And with the combination of volumes and instances that you can attach and mix and match together, there's a really big number of combinations that you can come up with. But I'm going to simplify it down into a few categories. I don't have any of my offload instance types up here. Some of you may be doing GPU or FPGA workloads. Those are available as well. But for the broad category of applications, I recommend you start with one of our general purpose instances. And so this could be the M5, T3, A1, even the upcoming M6G. And these have a pretty balanced ratio of CPU to memory. If your application is more compute intensive, say you need more CPU threads or higher frequency, we've got the C5, C5N, Z1D in that category, or even the C6G. If you need to go the other way, as a lot of databases do, we've got our higher memory instances, which have a much larger amount of memory. We've got R5, R6G, and even X1E and the U metal instances that have terabytes of memory. And the one thing that, if you've been around AWS and been using EC2 for a while, you'll notice that I'm focusing mainly on Nitro instances. And I think it's really important that if you're building an application today, and even with your existing legacy applications, that you migrate to Nitro as fast as you can. And there's a number of reasons why. We've done a lot of work to understand the workloads, understand how our data centers work, understand how customers use applications. And we have added things that make the platform more efficient. And so the Nitro system really boils down to three parts. We'll start in the center, and that's the Nitro security chip. And so this gives us a hardware root of trust. Lets us know that the hardware is what we expect it is, increasing the security of our platform. Also allows us to offer bare metal instances. And now I'm not going to go into a super deep dive on Nitro today. There are other sessions for that, and I highly encourage you to attend them if you want to geek out about some of the stuff. Our Nitro hypervisor, so we built it from the ground up. We started with KVM, but it doesn't look anything like KVM that's in upstream. We've highly customized it for our infrastructure. One of the things that we recognized is that if we offload all of our devices, we don't need any of the device emulation code. And so that greatly simplifies the hypervisor, and it removes a lot of surface area for security. The way that we did that was by building Nitro cards. And so we've got VPC networking offloads, we've got EBS offloads, instance storage, as well as our main system controller are all offloaded on Nitro cards. Now, since this is an EBS talk, I'm going to focus in a little bit on the EBS Nitro card. And so Ash just mentioned earlier that we can offer security encryption for EBS volumes with no performance impact on our C4, C5, or 4 series, 5 series, and our upcoming 6 series instances. And that's because of the Nitro card. So we've had these in our instances since the C4, but we didn't expose it directly. And one of the reasons why is that the NVMe interface that we present back in 2014 when we launched C4 wasn't mature. The driver stacks in the operating systems weren't mature enough. 2 years ago, we realized or noticed that the drivers were getting a lot more mature, a lot of bugs being fixed, a lot of performance getting improved, both in Linux and Windows, as well as the BSD platforms. And so we were able to take that one last remaining thing that we weren't able to present into the instance and move it into a PCI device in your guest. And so on the EBS backend, the Nitro Card does provide that encryption offload, and that's a hardware-assisted offload. And so all the crypto keys are stored in that module, not accessible by anybody. We implement the fad today is NVMe over fabrics. We've been doing it for a while. We present NVMe to the guest. We have some sort of fabric backend. Might not look exactly like you would expect, but it really is NVMe over fabrics. And this allows us to do this super efficiently over our own dedicated uplink, which gives us the ability to do EBS Optimized by default. And so EBS Optimized is a dedicated uplink. Gives you dedicated EBS bandwidth, up to 14 gigabits per second, or 1750 megabytes per second. And on smaller instances with Nitro, one of the things that we were able to do is provide burst capability so that you can actually burst up to a higher amount for some period of time. And Ashish will go into that later, what those numbers are, giving you the ability to use a smaller instance size, perhaps. Now, one of the things that we did, and I love this, that we're continually iterating, these Nitro cards have enabled us, with some software improvements, to now give you up to 19 gigabits of throughput per instance. And this is EBS Optimized. This is available today on your C, M, and R5 instances, and coming soon to the rest of the Nitro family over the next few weeks. So when you're building your application, it's really important that you don't just be stagnant. Continue to experiment. What we have today, what your application has today, you may grow, your application performance needs may change as you're scaling, you've onboarded more customers. So keep experimenting. Use the scientific method when you do it, though, so that you have repeatable processes. If you're using benchmarks, that's a great first step. It gives you an idea of the performance of your combination, but nothing works and really shows you the performance like your real-world workload. And so if you have the ability to do A/B testing or modeling your actual customer traffic, maybe it's a one box as well in a larger system, it's a great way to actually see if your changes have improved. Now, you can monitor your EBS volumes with CloudWatch. And so one of the things that's super interesting is we have a burst bucket metric. And this tells you for GP2, ST1, SC1 volumes, how your burst is doing and if you're utilizing it. And so I've got a workload here on a 500 gigabyte volume. And you'll see for the 35 minutes or 40 minutes that I'm getting that full 100% of my burst bucket. The burst bucket is depleting in the blue. And I'm getting the volume performance 3,000 IOPS there in the orange. And then when my burst bucket depletes, my IOPS trail off. I stop my workload. My burst bucket comes back. This is a really easy way to see if you're using your burst bucket, if you need to scale your volume or scale your performance needs. You can also combine metrics with CloudWatch. You can monitor a RAID set if you want, or other metrics of your application and provide a higher level view. And so on scaling, you can use elastic volumes to either get to the right type or get to the right performance level. Maybe you started with an IO1 volume, you realize that's more than you need. You can go to a GP2 volume. With GP2, just ensure that the size gives you enough performance for your workload. So you may need to scale the size up depending on where you're going there. So in EBS, we actually think about availability and durability separate. This is a little bit different than most people think about storage. But if you think about EBS as more of a distributed system, it kind of makes sense. We actually do think about it as a distributed system. And so EBS is designed for 5 nines of service availability. What do we mean by availability? So when we say availability, it's the ability for the instance to get to the hosts that store your backend data. So this accounts for the actual EC2 hardware, the network, and the physical hardware that stores the data. Now, once we get there, we think about durability. And so durability is the ability for us to actually get to your data or store your data. Now, EBS is designed for a failure rate of 0.1 to 0.2%. And the way to think about this is, on average, if you have 1,000 volumes for the course of a year, you can expect 1 to 2 of those volumes to fail. Now, knowing that failures happen, it's really important to think about how to design to accommodate that. Now, I mentioned earlier that I'd talk about what critical databases were and things like that. So in AWS and Amazon broader scale, we actually have built a ton of distributed systems. And we think about these systems in 1 of 2 ways. And the way that we bucket these is we ask ourselves this question: would my customers or my business be impacted by degradation or an outage? If the answer to that question is yes, we call it a tier 1 or a critical system. And now the question is, why would we bucket this? Why not build everything as a tier 1 system? The thing about tier 1 systems is there's going to be a higher cost involved. Either you're going to have an EBS volume that has higher performance characteristics. Maybe it's scaled for your peak instead of your average. Maybe you have an active-active or an active-passive or some sort of clustered solution. There's also a human cost. 5 nines of availability or higher is very little downtime. So you have to think carefully about your deployment strategies and how you're going to operate the system. And so we have the everything else bucket for things that might not be business impacting. And so this could be analytics, ETL jobs. Maybe there's a finance pipeline that can run at night so that it's ready during the day. And if you have an hour of downtime at midnight, nobody really notices, except for the engineers that have to actually deploy the changes in the middle of the night. So when your volumes fail, it is important to be able to recover your data. And so for that, we've got EBS Snapshots, which are point-in-time backup of the modified volume data. Now, these change blocks are stored in S3, which is a service with 11 nines of durability. EBS Snapshots are incremental and crash consistent. And one of the neat things that we released this year was the ability to take a crash consistent view of all of the volumes attached to your instance. So previously, you had to, one by one, take a snapshot of every volume attached to your instance. Now, with one API call, you can actually take a consistent snapshot of all of them. And so with Amazon Data Lifecycle Manager, you can actually automate this and reduce the amount of data loss in a failure, or improve your ability to recover from it. And so this automates your lifecycle, integrates with CloudFormation, and also integrates, you can do EBS volume or instance level snapshots. Now, once you have these snapshots, just a couple weeks ago, we released Fast Snapshot Restore, which gives you the ability to enable snapshots to have a higher recovery rate. And so this could be either snapshots or the proper pronunciation, which is AMI, up to 10 volumes at a time. And so you just create the snapshot, we hydrate that in the background, and then you'll get near real-time performance or near expected performance as we hydrate that. And with that, we'll talk a little bit more about ways to save cost on EBS.
Perfect. Discussion around performance and availability and durability. One of the things that we get asked by customers is, OK, so how do I save cost on EBS? As Mark alluded, we have 4 volume types. And really, selecting the right volume for the right workload is key. Because each of these volumes comes with a different cost point, right? So you have GP2 at 10 cents per gigabyte month, and all the way, and you have SC1 going to 2.5 cents per gigabyte month. And you can mix and match based on your workload, based on what's important. You can mix and match these volume types to meet your business needs. And that is a huge cost lever in terms of thinking about volumes. Mark mentioned elastic volumes. You can use elastic volumes to size your volumes correctly. You don't have to size for what you ultimately think you need. If your workload is going to scale and grow, you can start small. So you can start with an IO1 volume, with a limited number of IOPS. And then as your needs grow that IO1 volume in terms of capacity and in terms of IOPS, and as you need it, rather than all up front. And again, that changes your overall cost profile, right? And making that change is as simple as a single command, right? You can modify volumes and increase the size and increase the IOPS as your business needs it. One thing, when you do increase the size, and I see this quite often, is make sure that you expand your file system to take advantage of that new capacity. Right? And that's one thing that I do interact a lot with customers on that front. Another common pattern we see is selecting the right instance instance size to match their needs. So in this case, a customer has C4 2x large connected to a provision IOPS volume that's 10 terabytes and 16,000 IOPS. What's wrong with this picture? Well, the 2x large can do 8,000 IOPS. And what that means is it is mismatched to the volume that it's connected to. Now, the 10 terabytes might be fine, but you can see that the C4 2x large cannot take advantage of the 16,000 IOPS that's been provisioned to the provision IOPS volume. Here's one way to fix it. You could go to a C4 4x large, which does 16,000 IOs. And now you have an instance that matches your provision IOPS volume IOPS. You could go the other way. You could go to you could keep the C4 2x large and reduce the IOPS on your IO1 volume to match the instance. Right? Both of those options are available, but keep tabs of which instance type you're matching to your storage needs. We talked about optimized burst earlier as a benefit, but how does it work, and what does that mean for you as customers? When you think about Nitro EBS Optimized Burst, we've enabled it on our Nitro family, so our 5 family, i3EN, T3, Z1D. If these instances have sizes less than 4XL, then what we've enabled is this new capability called EBS Optimized Burst. Your burst IOPS and throughput can run up to 30 minutes every 24 hours, because we find that a lot of workloads need that short spike of IOs or bandwidth and can benefit by reducing the instance size. To get a sense of what that looks like, here's an example. So if your sustained IOPS are 4,000, right, but you need a burst capability for a half hour, you can use a C5 large, and that can give you that performance need that you have. Whereas without the burst, you would have to go to potentially, in this case, a C4 2x large, because 20,000 is your IOPS need. Right? So in other words, by balancing and understanding your workload and understanding sort of what that spike looks like, you might be able to go to a lower instance size, again, helping you save money. A third pattern is tagging volumes and snapshots on create. One of the things that we see is customers create volumes, they spin up volumes, create snapshots. Instances go away, the volumes and the snapshots remain. And then everybody's left asking the question, what was that volume doing? And what was that snapshot connected to? Right? Both volumes and snapshots, as you can see from the commands there, support tag on create. Use tags on create to make sure you understand what the purpose of that volume was, what that purpose of the snapshot was. And as your needs change, you now have trackability and traceability. You can also use cost allocation tags on your snapshots to keep tabs on how your cost changes for your customers. Show of hands, how many people know delete on termination? Few of you, but not enough, right? Delete on termination is a flag on a volume. So on boot volumes, it gets set to true by default. On data volumes, it gets set to false by default. But here's what it means. If delete on termination is set to false, when an instance goes away, the volume stays behind. When it's set to true, if the instance goes away, the volume also goes away. So if you have a workload in which your instance lifecycle matches your storage lifecycle, set delete on termination equal to true, right? but use with care, right? You may delete volumes that you might actually need. So it is super important in this case that you understand how your use case is and what your lifecycle needs are. Data Lifecycle Manager, again, this is something that we launched last year to enable customers to keep track of their snapshot and set policies on snapshots. You can set policies based on taking snapshots in the periodic interval and then keeping certain counts of snapshots. So here's an example of a policy that I set, which is it's taking snapshots every 2 hours and keeping track of 24 snapshots, which gives me 2 days of snapshots, right? And that way you have a lineage that's fixed and gives you an upper bound of how long your snapshot lineage is. Our customers came back to us and said, well, we need more. We want snapshot retention that is based on the time that the snapshot exists, and that's precisely what we've launched. So this is now available. We now have time-based data lifecycle manager policies, where you can now select snapshot retention based on days, weeks, and months. And this allows you to meet your business needs. So in the same tab that you selected policies, you can now select time-based policies and do a count based on days. And so this sets the upper bound on how long a snapshot can be retained. OK. Another thing you can do is lower cost on the volume type if the volume is not in use. So if the instance dies, or you terminate the instance, you can move your GP2 volume and store it on SC1. And when it's time to connect the instance back up again, connect it to a GP2 volume, or elastic volume, use modify volumes to move it to a GP2 volume. And the way you would do this makes it such you have to keep track of certain things. One is there's a 6-hour EV time limit, and the amount of time it takes to modify volumes. This is especially helpful if you have a predictable schedule, right? Either weekends or month ends, and something that you can plan for. The last piece, delete volumes that you don't need. Now, I always put the use with care tab on it because you need to understand your use case and your patterns. But in this case, figure out if you have a volume that's detached. In general, you can use CloudWatch events or tags to figure out how long these volumes have been detached. Set an explicit organizational policy that says how long you're going to keep volumes detached. We strongly advise that you take snapshots of these volumes, and then you can proceed to delete them. Right? These are all sort of techniques and patterns that we see customers employing in order to get to lower cost points on their EBS bill. So to put all these best practices together and to give you a sense of sort of how they use EBS, up next is Teradata. Vinod Mahesh.
Thank you, Ashish. Hey, everyone. I'm Vinod Raman. I'm the product manager for Teradata products on AWS. To give you a quick overview of who's Teradata, Teradata pioneered the data warehouse 40 years ago, and we've been a leader in this space ever since. Right now, we are focused on delivering Teradata products as a service on AWS to our customers because that's what our customers want. In fact, we have multiple production customers running today on AWS. Our customer segment spans multiple verticals here. Many of our customers, the common characteristic here is that they have very, very demanding needs: high availability, resiliency, and performance at scale. Our core product on AWS is called Teradata Vantage. So the Vantage value prop is pretty simple. We want our customers to use any tool, any language of their choice to access 100% of their data. And the core of Vantage here is 3 engines here. The Advanced SQL engine, which is our Teradata database, and we've also added machine learning and graph engine. Also, the heart of the system is the data store. The data store is very important, plays a central role here because all of these 3 engines must be able to hit the same data store so that you can unlock more value out of that data there. So different use cases that we see for Vantage on AWS: production analytics, where we have at scale, millions of queries, hundreds of users, thousands of users, hundreds of applications running at scale. Discovery analytics, where data scientists want to explore the data located in their S3 buckets, or test and dev systems, where line of businesses want to spin up systems and quickly try out new things. Disaster recovery is a huge use case for us as well. As we see customers migrate from on-prem to AWS, they want to do business continuity, and then having a second system on AWS is a great way to achieve business continuity. Coming down to the technical details of things here, our Vantage software runs on EC2 instance. To emphasize the point here, Vantage does not just leverages one storage type, but multiple storage types. By that, I mean, depending on the needs, it can either use memory, EBS, or S3. So for frequently accessed data that are accessed quickly and then performance is very critical, memory is leveraged, including local memory plus NVMe memory if the instance supports that. EBS we use for persistent data that needs to be updated quite often, but you still need performance SLAs on it. And then S3-based data lakes, if data scientists and others want to query a large amount of unstructured data in data lakes. Couple of points I want to emphasize here that was made earlier, the right choice of instance types. We choose our instance types first based upon a couple of factors. Number one, how many vCPUs an instance type has, how much memory per vCPU is available, and how much throughput or bandwidth to EBS is available on a per vCPU basis. We originally started off on the 4 series of instances, and we've recently switched pretty much all our deployments to the 5 series of instances, and we see a big difference in throughput and performance. And it also sets us up to get the latest and greatest as AWS innovates, and we partner with them, including the latest recently announced 19 gigabits per second throughput EBS. So it sets us up to receive the latest and greatest from AWS by choosing the Nitro family of instances. With that, I'm going to hand it over to my colleague, Mahesh.
Thanks, Vinod. Good morning. My name is Mahesh Subramanian, and manage the engineering and operations for Teradata Vantage as a service on public cloud, AWS specifically. I'm going to be talking about how we chose the EBS volume type and also some of the EBS capabilities that we use within Vantage. But first, wanted to start off just with a recap that Teradata Vantage is a very critical system for our customers. It's a source of truth. And most of the business critical data is stored in the SQL engine, and the analytics is actually performed on that particular data. So that system is very critical. So for availability, how we solve it is we have multiple copies of data on both EBS and S3 to solve for both local and zonal failures. To understand how we chose the EBS volume type, we need to understand the workload characteristics. The Teradata Vantage workload characteristics tend to be CPU intensive or memory intensive or throughput to storage intensive. A use case for a CPU intensive would be IoT sensor related workloads. Memory would be machine learning related workloads. And complex SQL queries are typically the throughput, throughput to storage related workloads. But the key here is the other is the workload profile. The Teradata Vantage workload profiles tends to be 90% read, 10% write. But the most important part is we look for a balance. The key word again is balance of high throughput and IOPS. So based on those considerations, we went with the GP2 SSD volumes for Vantage for the best price and performance for our customers. Now, if we compare it to some of the other volumes that were discussed, it's important to note that Teradata Vantage, the I/O size is typically 96 KB with a range of 4 KB to 512 KB. That means it is typically small and random nature of I/O. And because of that, the ST1 EBS volume type does not have the necessary performance because of the random nature of I/O that we have. The IO1 is very performant, but the price and consistency that it gave is not required for a system like Vantage. And therefore, again, because of the balance, we went with GP2. Now, let's just I want to talk about a couple of services that we use and capabilities that we use from EBS. The first one is expanding volumes, EBS volumes using the APIs. This has been a very useful feature for us to expand the volumes of our customers without having any downtime. So earlier, we had to redeploy clusters for them. We don't have to do that anymore because of this particular feature. And we have been an early adopter of this from AWS. More recently, we have been now working with crash-consistent EC2-wide snapshots. It helps us with faster and smoother backups. And early tests have been showing that we have been able to give a faster RPO for our customers. But what I've liked about this feature is, and this capability is the other aspects, other capability or other use cases that it can be used for, specifically around disaster recovery to meet specific RTO, RPO SLAs for our customers. Finally, I wanted to invite you all to our booth. Teradata booth is number 405. As you get into the expo, it's on the left-hand side. We have Teradata Vantage presentations and demos there, and of course, swag. Thank you, and over to you, Ashish.
All right, almost to the end of our journey. We have training and certification that's available for you. There are free digital courses on storage and the entire storage family. Do take them. Thank you for being patient through the session. And Mark and I and the Teradata team will be around here. Please stop by to ask any questions. We take your feedback very seriously, and we've put a lot of effort into sort of corralling this based on your feedback. Please complete the survey in the mobile app. Look forward to your feedback and your questions. Thank you for being EBS and AWS customers. Thank you.